everybody, I'm Jana Novotná and I'm going to present you our joint work with Jan Kratochvíl and Tomáš Masaryk about the bubble model for mixed-unit interval graphs and its applications. We are interested in intersection graph of geometrical objects. One of the most basic and long-studied intersection graphs are intersection graphs of segments on a real line, so-called interval graphs. And if intervals are restricted to a unit length, we obtain a proper subclass called unit interval graphs. Let's look at a quick example of CLO. CLO is an interval graph, as you see in the picture of a given interval representation, but it's not a unit interval graph. And in our paper, we consider another proper subclass of interval graphs, which is a generalization of unit interval graphs. So, for instance, it will contain CLO. And I'm going to define it in the next slide. Intervals can be open, closed, or semi-closed. And if we speak about interval representation, originally no particular attention was paid to which type of interval is used. It has been shown that this is of no importance as far as interval graphs are concerned. But if you restrict the intervals to unit lengths and allow to use more types of intervals, then this small modification captures a much richer class of graphs than just unit interval graphs. So for instance, if we are allowed to use both open and closed intervals, we can get a unit interval representation of a CLO, as you see in the picture. The biggest class among such graph classes, so the one allowing all types of unit intervals, is called mixed unit interval graphs. And this is the class we care about in our paper. Just a small note, although there are 15 different possible combinations of types of unit intervals, several researchers have proven in past years that it leads only to 4 different classes. The smallest one is the class of unit interval graphs, as defined in the previous slide, and the biggest one, as I said, is the class of mixed unit interval graphs. There are lots of characterizations of interval and unit interval graphs. One of them is a matrix-like representation by Hegernes, Meister, and Papadopoulos called bubble model. Similar notion was independently earlier discovered by Lozin. He called it a canonical partition. And we generalized this notion for mixed interval graphs, and we obtain similar characterizations that a graph is mixed in the interval if and only if it has a bubble model. So what's a U-bubble model? In the U-bubble model, the vertices of a mixed unit interval graph are placed into a matrix-like structure. We call the structure U-bubble structure and its entries bubbles. And each bubble may contain more vertices as well as it may be empty. And moreover, each bubble is split into 4 quadrants, which corresponds to the types of intervals as it is connected with a mixed unit interval representation. And you will see more intuition behind on the next slides. The point is that the edges of our graph are then represented implicitly by the position of vertices in the structure. So therefore, the position of vertices encodes the whole graph. U-bubble model is a representation of a graph which is given by the position of vertices in such a structure by the following rules. UV is an edge in our graph if and only U and V occur in bubbles which are either in the same column or in the consecutive columns where the left bubble is lower than the right bubble, or they are on the same row, but then the left one belongs to the quadrant corresponding to an interval with right endpoint closed, and the right one belongs to the quadrant with left endpoint closed. So overall, there are these edges. Each column is a clique, and then you find all the edges here going everywhere above to the next column, and you find edges between specific quadrants in the same row. And then there are some more formalities, like no column ends with an empty bubble, or the first non-empty bubble is not higher than the first non-empty bubble in the previous column. But those are just technicalities. This representation has almost the same structure as the original bubble model, except that edges are allowed in the same row under specific conditions. And of course, we distinguish the 4 quadrants. Here you can see just a small example of a graph and a bubble model for it. And as you may wonder, a graph can have more bubble models, so this is just one of them. Once you know the definition, I remind our theorem, which says that graph is mixed unit interval if and only if it has a U-bubble model. And moreover, the U-bubble model can be constructed in linear time in the number of vertices if a mixed unit interval representation is given. And if not, it can be constructed in quadratic time thanks to the result of Kratochvíl and Talon, who mentioned that a mixed unit interval representation can be created in quadratic time. So I will show you now the basic idea of the U-bubble model construction. So as I said, the algorithm uses a mixed unit interval representations. So once we have it, we can work with the intervals. So at first we put all the vertices which are represented by intervals in the same position into the same bubble. And we put them into a particular bubble quadrant according to the type of their interval in the representation. So if the vertex is represented by open interval, for example, K in the picture, we put it into the bubble quadrant which corresponds to open intervals, and so on. Then we need to find the positions of the bubbles in our structure. That means to which column and row they belong. And the idea is quite simple. The mixed unit interval representation gives us an order of the intervals. Maybe just don't be confused that I'm speaking about the intervals instead of bubbles, as bubbles are characterized by the intervals inside. So once we have such an order, we go from left to right, and at first we put the first interval to the first column and row. So it's A in the picture. Then all the other intervals which share more than one point with the first one belongs to the same column below. And once we find an interval that shares at most one endpoint, that endpoint must be, once we find an interval that shares the endpoint with the first interval, so with A, we set it as the first one in the next column. So, but to what row? We put it to the same height if the position of its left endpoints equals to the right endpoint of the first interval, or we put it below if it's not the case. And we do that similarly for the other intervals in its column. So we assign the row as before based on the previous column in such a way that all the intervals that do not share any point with our new interval will be above. If there is some interval in the previous column that shares just the endpoint with it, it will be in the same row, and all the intervals which have a bigger intersection will be lower. So let's do 2 more steps with E and F. So as you see, it will be under A, and of course under D, and above B. So here, look at it. It will be on the same level as B, as they share endpoints. In this way, we create the whole-wiki bubble model, and we just need to do the assignment of rows carefully to obtain clear linear time algorithm. So in fact, we go through the representation twice. At first, we assign just columns and create some auxiliary marks, and in the second time, we assign rows. That was the more complicated implication, and for the other implication, you can realize yourself that it's quite uneasy to obtain a mixed unit interval representation from a U-bubble model. U-bubble model gives us a nice structure to work with, for example, to compute click width. For those who don't know what click width is, it's one of the most studied structural graph parameters, and many hard problems become polynomial time solvable on the classes where this parameter is bounded, which is unfortunately not the case in mixed unit interval graphs, as in general unit interval graphs have unbounded click width. So I won't tell you the definition as it's not crucial in my talk, but instead a take-home message is that we can bound click width by properties of U-bubble model. So in particular, we can upper bound click width in terms of the number of columns or the number of rows. And as another application, we obtain a subexponential time algorithm for the problem of finding maximum cut, and I spend the rest of my presentation with it. So at first, I would like to define the MaxCut problem. So for a given graph, the goal is to find a vertex partition into two sets, such that the number of edges in between is maximized. So in other words, you split the vertices into two sets, count the number of edges between them, and this number should be the largest possible. So let's move to the complexity of this problem. It's NP-complete in general. And the question whether it is polynomial or NP-hard on interval or unit interval graphs has been in interest of many researchers for a long time. A polynomial algorithm was claimed by Bodlander, Klocks, and Niedermeyer in 1999, but they later withdrew it themselves. Another attempt for polynomial algorithm was done by Boyachi, Ekim, and Shalom in 2015. And this was a paper which started our research in this direction, as it was to our best knowledge the only well-known problem for which time complexity differed in interval and unit interval graphs, as it was unknown in interval graphs but known to be polynomial in unit interval graphs. So therefore there was a chance to extend this result to mixed unit interval graphs and see more where the complexity lies. Unfortunately, we claim that this algorithm is also incorrect, and you can find the explanation in our paper. And also our effort to find another polynomial time algorithm ended with no success. So the message is that the question whether MaxCut problem is polynomial or a polynomial time solvable or NP-hard in unit interval graphs is still open. Instead of polynomial time algorithms, some of the ideas of the mentioned paper by Boyachi was used during workshop discussions to obtain at least subexponential time algorithm for unit interval graphs, which can be extended also to mixed unit interval graphs. So there is a subexponential time algorithm for mixed unit interval graphs. And interestingly, at the end of this May, a paper about NP completeness for interval graphs has appeared on arXiv. So that's a part of the history and also a motivation of our work. And now I would like to speak about the subexponential time algorithm itself. So to be more concrete, we show that MaxCut can be solved in this time on an n-vertex mixed unit interval graph. And I will tell you the crucial ideas of the algorithm on the next slide. What also flows from the algorithm is that the MaxCut problem can be solved in time O of n to the number of columns of a bubble model. So look that this gives us a polynomial time algorithm if the number of columns is fixed, is bounded. In other words, using the speech of parameterized complexity, the MaxCut problem is in XP parameterized by the number of columns. We obtain a similar result also for rows, thanks to the result of Fomingal, Vachelok-Stanov, and Sabra, who express running time in terms of click width. So combining it with our upper bounds for click width, we have running time which is dependent also on the number of rows, and of course on the number of columns as well, but with slightly worse time than the above one. I would like to spend a few minutes with the Subexponential time algorithm itself and show you crucial ideas there. So, not surprisingly, we use a bubble model, and just to remind, we want to partition the vertices there into two subsets such that the number of edges between them is the biggest possible. To be able to speak about it, I will call one of the sets cut set. So, how we proceed? At first, look at the columns which contain at most square root of n vertices, so these orange ones, and observe that we can afford to do brute force algorithm in such a column as it does not exceed the times 2 to the square root of n. Also observe that most of the brute force orange column guesses are independent of each other. As once you know the cut in the previous column, it does not matter on how the cut looks like in the columns before. So that also means that those orange columns split our graph into several white blocks, and therefore we can solve the white blocks separately if we know the cut on their neighboring orange columns. So consider now just one remaining part with a fixed cut on its orange columns, and we will use a dynamic programming approach to find the maximum cut there. So what we do, we process bubbles one by one in top, bottom, left, right order. And imagine we have already processed I-1 bubbles and we are up to add another one. At first, I will mention a key observation. So look at the step where we are adding a new bubble. So where exactly are the edges in the process graph? So there are some edges inside the already processed graph. There are all edges inside my new bubble. There are all edges between my new bubble and its column above. All edges between my new bubble and the next column above. And all edges between specific bubble quadrants of my new bubble and the bubble next to it in the previous column. And then also, if your bubble is from the first or last column, there can be also edges going here and here. But what's important is that for each bubble we need to know how many its vertices are from the cut only in a while when we are processing it. So when we are processing a bubble, we consider all the possibilities of numbers of vertices from cut in each quadrant. But later we can count the number of cut edges with knowing only the numbers of cut vertices in the columns in the already processed part. So that means without knowing exactly which vertices belong to the cut. Therefore, for each column, it's sufficient to remember how many vertices from the cut are in the already processed part, with a small exception that we need to remember also the number of vertices from the cut in the specific quadrants in the last processed bubble, just because these edges. And as there are less than the square root of n columns, this leads to n to the square root of n possibilities. And for each such possibility, we remember the best cut. So that is the base idea. And from this, you can also observe the corollary about the expression using the number of columns. It was asymptotically n to the number of columns plus 5. And now it remains to put everything together and play with technical details, and also to conclude my talk. So thank you for the attention, and if you have any questions, do not hesitate to contact us.